So let me give you some short history and some definition of what exactly we mean by semantic SLAM. Before saying the word SLAM, I might say word odometry. What odometry is really measuring how much you have gone from one place. If you start at one point, how much and at which position you are with respect to your original point. And this is something that it has been used in the past when people were not having a GPS by either throwing breadcrumbs or holding a thread in a labyrinth. And there is a lot of stories about how you can get lost and how to find your ways. And in computer vision, where we showed that we can solve this problem without GPS and using only one camera, and might be an accelerometer and a gyroscope, which together build an IMU. So what you see on the left is the Nanotechnology Center, and on the right you see the path that we had by just going around with a GoPro and an attached IMU. And if you solve the visual odometry, you can really solve a problem. For example, go 100 meters at 30 degrees bearing and return to the same position. Or let's say you don't have any data connection, then you can leave like your hotel somewhere, and then you can have this path and follow this path back to your original home position. And this technology now, there is research about this of 30 years, and we have contributed with several algorithms, and now it is really available at every phone. All the toolkits that do augmented reality support this visual odometry technology, namely the AR kit and the AR code in the iPhone and the Android phones respectively. So, and you can do it, for example, by taking a second camera and having a stereo camera. And the way you do it is with really these features you see on the left, which might be either points or small line segments on the top. And with using, if you have also a laser scanner with you, you can really build also a map of the environment. So not only you have your path, which is the localization, but simultaneously you are building a 2D layout map. That's why we call it simultaneous localization and mapping. And we emphasize the visual when we don't use any LiDAR, or when we don't use when we don't use any GPS. So this gives you a metric map. Metric map means that if we wanted to, you can solve the problem I said, like go like in this direction, like a 2 o'clock direction for 20 meters. But the main problem with that is that people do not communicate this way. So you can never say, oh, let us meet at like GPS position, or we don't say, let us meet after you enter the entrance at coordinates 10,5, all right? So usually we communicate about directions by using semantic information. For example, you can say, fetch my shoes, they might be underneath one of the chairs at the table, all right? If you tell this to any human or even a robot. So, and all the maps you see around, actually the actual maps like in cartography, they don't have only metric information these days. They also mention shops, they have buildings, they have annotated roads, and some of them also, they have very detailed information now like traffic lights. So while metric information is basic for some problems, and animals use a lot of like metric information, but even animals use landmarks, like things that they stay in their memory. For us people, they might have this semantic information. We have a word for it. For the animals, they just have a saliency. And another way, another use of it in terms of not only of communication is that if you have a robot, not only you can give a direction like navigate to the opposite room corner unless you see a cart, in which case position yourself in front of it. And this is an example of what we call a reactive navigation. But also you can really abstract the environment. Instead of having all these little points you see in point clouds and the small breadcrumbs from the visual features, you really have just these polygonal objects, which you can see here on the upper right, and which you can recognize and position exactly in space. And this is really the task of semantic SLAM. Not only finding your path, but also at the same time recognizing the objects and putting them at the right place where they belong in the environment. So why is it hard, and why is it not yet, for example, on our phones? Oh, this is another application more recently where in terms of reinforcement learning, how you can build a semantic navigation policy. You see, this is not only where is its object after we have done the semantic mapping, but also the relation, the context of these actually objects to each other. And why is this hard? For a while, it was very hard because we couldn't do good recognition of objects. But now with advances in machine learning, in deep learning, and having all the hardware like the GPUs, we can really very successfully build boxes around cars in the environment. So our measurements are not only just the little features, but also these bounding boxes for every object class. The problem, though, is that we recognize that there is a car, but we don't recognize the particular instance or the particular ID of the car. So we really have a problem of data association. When we have multiple doors, like here on the upper left, or multiple chairs, and we take a camera image, and then we have a map of those, we don't really know which chair corresponds to which one. So we have really a combinatorial matching problem. And if any of you are in my department in computer science, you know that this combinatorial problem might have even exponential complexity. And if you don't solve this problem in the right way, and you just follow what we call a greedy solution, like just choosing for the next best association without looking ahead or without having a global optimization, then instead of building this map on the left, then you might build this quite distorted map on the right. These distorted maps are usually built because when you come at the same place, a problem called the loop closure, you don't really recognize that you're at the same place. So you think it is a new place. And even humans have this problem. Like when you are driving around and everything looks the same, you might not recognize whether you're back at the same place, you close the loop, or you're at the new intersection. So this is a combinatorially challenging problem, and this is really what the main contribution of our paper, in addition with the whole system that we have built and we're going to show next. Now, in the demonstration, the problem is that it's highly ambiguous if we detect only these boxes. And it would really help if instead of only having the boxes for dissociating, we have also the exact orientation of the objects in 3D, so that we have the occupancy of this object in 3D, and we can really much better, if the object hasn't changed pose, really resolve these ambiguities. And to achieve this, so this is like a kind of the system that we have, we have images here, Y, we have inertial information, accelerometer, and gyro information. We have this database of images annotated with cars and or chairs or doors. And output, we have the sensor states, which is your location and orientation, and then the semantic map, where is its object in the environment. And what we really want to achieve is really to have the most stable actually position and orientation of the object. And when we realize that this can really help also in the data association, we employed a method which is not just a box, but a more detailed description of the shape of the object. And this way, not only we found the orientation, but we also really reconstructed the whole shape if we had a database of CAD models of cars or chairs or tables. So this is achieved with a deep learning architecture called UNet, and we can you can concatenate several units. The output is these are called heat maps, where every of these key points is really the maximum of these heat maps. And these are called semantic key points because they associate it always with a particular class of the objects. There's different semantic key points for cars, different semantic key points for the tables or the chairs. And this is an example of a chair. And if you have the semantic key points and you have a database of objects, you can really reconstruct the exact also size of the chair and the exact shape and orientation. So this is really the whole software, like in terms of software package we are using, and we will make this also available in order to think about in terms of information flow. You have the camera here and the IMU, and this can be really a camera and an IMU running on your phone, okay? Which these are really, the phone now has the best camera you can find available. And we are running on this phone first an object detector. It gives you a box. Inside this box, we find these key points. And these two go together to what we call an object processor, which really computes, takes as input also the database of the shapes that we have for every object. And on the other hand, we have a feature tracking, which is really this small visual like breadcrumbs you see around, like small features on the scene, and takes the inertial integrator from the accelerometer and the gyro. And this goes into what we call an odometry processor. And together they go into an optimization engine, which really smooths the trajectory and find really the most optimal both trajectory of the camera, which can be mounted on a robot or it can be handheld. You can hold in your hand, or and also recognizes this very important, recognizes these loops when you have been at the same place. So X here is your trajectory, and L is all the semantics of the scene. So this is to give you, to now you understand better actually what is going on. This is the original image here on the left. You have these bounding boxes for a set of classes of objects. Inside this every box on the upper left, on the upper left, you see the visual features that we have both on the boxes, but also other visual features in the scene. And then on the right, you see the result, which is the trajectory. It is the objects and these visual breadcrumbs around, which really help the robot orient itself during the whole time, and particularly when the robot does not see any object that is in its own database. And this is a really collaboration with the lab from Dan Kodicek, who built actually this the planning part of this system, because it is really can even if things change, or even if you don't see things where you're expecting to see, it can really replan its trajectory. So this is another example from inside Innovation. I think again with a camera mounted on a robot, you see the objects here reconstructed. The moving three fingers are the orientation of the robot, and all the red things are really visual features around in the environment, which help the robot find its own trajectory. So here, this is an example from a sequence from outside. This is a camera mounted on a car, and the objects that are recognized here are only cars. You see we first show the box around the car, and soon, and you see on the bottom, you see all the semantic key points of the cars and the orientation of the cars. You see that here on the left, the cars were orthogonally parked, and this here are parked parallel to the street. And you see that the system is not perfect. Actually, we miss a few cars there. And we also reconstruct only the cars that are parked, not the moving ones. But you get a really pretty good idea here what the system really does. So we have written several papers about it. Both George and I were really very proud of Sean and Nikolai because they received the best conference paper award at ICRA 2017. This is the International Conference on Robotics and Automation, the main robotics venue in the world, and to be the best among the 1,000 papers is really a big honor, and we're really very, very proud of Sean and Nikolai for this achievement. We have also filed for a patent, as you see below, and we are really very proud that our technology has been selected to be candidate for the Y Prize. And I am open for questions.
Thanks, Professor. Is there take a couple questions for?
I have also the chat box open if anybody wants to write something.
Professor, I have a quick question. So very interesting technology for yourself. So I wonder, just in this example, I'm wondering if this camera device come back to do the same loop again, does it recognize the cars as the same car that it has viewed before?
Yes, exactly. So that's a very good question, and it really shows the transition also from the first original system where we just recognized boxes with cars. In our case, we match the car with the same shape, and we can detect also shape deformation. So a Toyota Camry has a different shape than the Corolla. All of them are really like deformations of like a dictionary of car shapes, and we can recognize that it's exactly the same. That is again a Camry. We could use also color if you want. We don't use it yet. We use only geometric information, and we definitely not use the ID of the car, right? But if it is something of exactly the same shape, we can do it now. I think for the color, it is even easier to do as an extension. Was this the question?
Yeah, thank you.
So there is a question. Roshan has a question in the chat. Is the system able to be performed on board the robot? So the system is able to be performed if you have a GPU, even like a Jetson or like one of these portable NVIDIAs. It cannot run only on the CPU because of the deep learning pipeline for the semantic key points and for the boxes. But right now it runs in real time, like 30 frames per second. So as long as you have this like in portable NVIDIA and a good CPU, not necessarily the one which is on the Jetson, like in one of like this portable, like the Nook from Intel, it will have no problem.